Okay, so we're continuing here in section 1.1, a little bit of review. Last year we did do some work with objects moving in 2 dimensions, and we ended up with displacements that were so many degrees north of east or something like that. So we're going to do a review of that uh, and extend it a little bit here in grade 12. So we're talking about 2-dimensional motion. So objects travel in more than 1 dimension. So here, for example, is an object. Starts here at this point here, initial position DI, ends up right here, right? Final position DF. And let's say its first motion was right here, so it started and then it got to here, then changed direction a little bit. Through its second displacement, went through this motion, got to here, then changed direction a little bit in its third displacement and got to there. So its total displacement or its resultant displacement would be adding up each of these three individual displacements. So the resultant displacement or the total displacement is the first displacement plus the second displacement plus the third. Now, if you had a fourth or a fifth or a sixth one, you'd keep on adding. But in this one, we only have 3 displacements. And I have a green vector here showing you what the total or resultant displacement would be. You simply draw a line. You start at the initial position, you end at the final position, you draw a line, it's in green here, and you put an arrow showing the direction from initial to final. So even though the object never went along this green total or resultant displacement line, that is the mathematical reality of what the difference is between its final position and its initial position. It's shown by this green arrow here. It's so many meters away from the initial position in a particular direction. But how would we find that if we're adding vectors? We're not adding numbers like 1 plus 2 plus 3 equals 6. It's not like that. These are vectors. They have to be added differently. And we did look at this in grade 11, and we're going to review it right now. So in grade 11, we would have done a question that involved vector tip to tail addition, VTTA. And it involves a situation where you have established certain directions. Okay, up the page is north, to the right of the page is east, so we've established that. And an object starts right here at its initial position. It goes through its first displacement, so it's traveling north. Then it changes direction and starts with the second position, and then object finally ends up right here at its final position. And we join the initial position and final position with a vector arrow, always points from initial to final, and that would be our resultant or total displacement. This is showing you how far you are from where you started. Where is final position with respect to initial position? Well, I'm so many meters away from the initial position. And it also tells you in what direction are you, because it's most definitely a vector. And we studied this in grade 11, and we use Pythagoras to find the magnitude of this side right here. And then we use tan inverse of opposite over adjacent to find the angle right in here. And we would get an answer like the resultant displacement is so many meters, theta degrees, east of north. This is east of north. We did this in grade 11. Now, the object never actually traveled along the green line that represents the resultant displacement. It traveled along the lines in black here. But nevertheless, if we want to describe where it is now compared to where it was, we use the green line here as a resultant displacement. We can tell whoever is interested how far the final position is from the initial one and at what angle. And we studied that in grade 11, and we did some questions out of the textbook. But now we're in grade 12, and things are going to get a little bit more complicated. In grade 11, we always established north and east. We're still going to do that. But in grade 11, all of our displacements were at 90 degrees to each other. They were all north-south and then at east-west. We're in grade 12 now. Our displacements, here they are, delta D1, delta D2 as well. they're not all at 90 degrees to each other. They're not always lined up northeast, north, south, east, west. They're at odd angles, right? You've got all these odd angles here. So we're going to need more advanced mathematics to calculate what the resultant displacement is. If this is the initial position and this is the final position, and we want to find out the difference between where you are now compared to where you were, that is the resultant displacement, we can't just stick to tan inverse and Pythagoras. We can't do that anymore. We got to start using things like cosine law and sine law, or come up with a completely new method, and we will, called the component methods. And the component method is one of the most important parts of this year's course. And we're going to look at that in greater depth. So here's a question similar to one we did last year, except not everything's at those very nice 90 degrees. Not everything's north, south, east, west. So let's take a quick look at this. A car travels 300.0 meters, 60 degrees north of east. 60 degrees north of east. So where is that? Well, it's the red vector right here. And here it is. It travels 300 degrees, excuse me, 300 meters, 60 degrees. Well, that's an awful 6. That's better. 60 degrees north of east. So that's its first motion, right? Then from there, it changes its direction. Then it travels 400 meters, 20 degrees south of west. So I've redrawn a Cartesian axis here, and here would be your 20 degrees south of west. It does that. And it does this all in 80 seconds. And we want to calculate the resultant or the total displacement and the average velocity. Well, the object started here, so there's your initial position. The object ended up here, so there's your final position. All right. So in yellow here, I have the displacement resultant vector. Starts here, ends up here. Here's this vector in yellow showing the total or resultant displacement. Well, just like we did last time, we have to do vector tip to tail addition. The resultant displacement is equal to the first displacement plus the second displacement, and we plug in the values that we have here. The first displacement, 300.0 meters, 60 degrees north of east, plus 400 meters, 20 degrees south of west, and you would have to add these up with vector tip to tail addition, except now, since we're always using what we call the angle magnitude version of these vectors, here's the magnitude, there's the angle, here's the magnitude, there's the angle. In order to do vector tip to tail addition, you would have to take a look at this diagram here and do a whole bunch of geometry and sine law and cosine law to figure out angles here, there, and everywhere. It could be done. It could be done using the diagram and vector tip to tail addition, and you would eventually calculate displacement resultant, the resultant displacement. It could be done. All right, remember, we're not just going to add 300 and 400. It doesn't work like that. It's vector tip to tail addition, but made more difficult because we don't have these 90-degree angles anymore. We'd have to use complex things, cosine law, sine law, geometry, Z rules, parallel rules of angles, opposite angle theorem, all those things we'd have to use in order to find delta dr. It would be more complex. What about if I told you there's a different way that's more straightforward? And it is looking at these vectors but describing them in components of x and y. Let's take a look at that. So here we have it, the component method. Very important. You'll be using the component method for the entire course. This is very important. Why? Because any vector, not just displacement vectors, any vector you can think of, displacement, velocity, acceleration, force vectors, you name it, any vector can be written as the sum of two perpendicular vectors in 2 dimensions. So for example, displacement vector that's the resultant is equal to the first displacement vector plus the second displacement vector. Now, each of these vectors here can be written as the sum of two perpendicular vectors. So displacement vector 1 can be written up as an x part of displacement vector 1 and a y part of displacement vector 1. Displacement vector 2, it can be written as an x part of displacement vector 2 plus a y part of displacement vector 2. So I'm going to remind you of this statement. We use it the entire year. Any vector can be written as the sum of two perpendicular vectors. Here it is, right here. X and y are perpendicular to each other. X and y are perpendicular to each other. So that first statement is what I've written in these two brackets. So let's take a look at each of them in turn. Here is that first vector. It's in red, displacement vector 1. It's 300 meters, and it's 60 degrees north of east. Now this red displacement vector 1, it can be written as the sum of displacement vector d1x component plus vector tip to tail addition plus displacement vector 1 y component. So this red vector is actually a sum of this x blue vector tip to tail addition with this blue y vector, blue x vector and blue y vector. These two added together are delta d1. Now when we look at it, we see that there is a trigonometric relationship here. That opposite of this angle is the magnitude of the y component, and the hypotenuse is the magnitude of that 300 meters. So that's what I've written right here. Sine 60 degrees equals opposite over hypotenuse. Opposite being the y component divided by the hypotenuse. Then I rearrange this equation. And I get the magnitude of this y component for delta d1 is equal to the magnitude of the entire vector times 60 degrees, and I do my calculating and I get 259.8 meters. Now, that's just the magnitude. I got to turn it into a vector. Well, what's the direction of this vector right here? Well, it's all in the y direction. So it becomes positive 259.8 meters y hat. Similarly, I can find out the x component of this delta d1. I take a look at it and I set up this trigonometric relationship. The cosine of 60 degrees is equal to the x component of this vector divided by the hypotenuse, which we know is 300. So I rearrange this. I know that delta d1 is that 300. It's the magnitude of the hypotenuse side. I multiply it by cos 60 and I get 150 meters. Now that's just the magnitude of that displacement vector d1 x component. I want a whole full-blown vector. Well, look, it's pointing in the positive x direction. So the x component of the first displacement vector is positive 150 meters x hat. So literally what I've done is I've translated angle magnitude, and angle magnitude for this vector was 300.0 meters, 60 degrees north of east. That was the original way of writing it. But now I'm going to write it as an ordered pair, as components, the component method. I've translated it into a new way of expressing the same information, and it's plus 150.0 meters x hat plus 259.8 meters y hat. So these are two different ways of expressing the same vector. They are equivalent to each other. 150.0 meters x hat plus 259.8 meters y hat is the same as saying 300 meters 60 degrees north of east. We've converted it. Similarly, here is the second displacement vector, delta D2, right? There it is, delta D2. And it was 400.0 meters, and it was 20 degrees south of west. There it is. This is the angle magnitude form of this vector. We're going to convert it into components. So I take a look here, and here is the x component of this right there. I'm going to find its magnitude. So we're still using trigonometric functions, right? And we get delta d2 x component is equal to delta d2, the entire 400 meters, times the cosine of 20. Why cosine of 20? Because this side right here, delta d2 x component, right, is adjacent to the 20 degrees. So since it's adjacent to the 20 degrees, we use cos. And we get that the magnitude of this side right here is 375.9 meters. But I want the entire vector itself, so I got to give it a direction. So we still get the 375.9 meters as the magnitude, but now I got to look at this direction right here. It's pointing in the negative x hat direction. So the x component of this vector is negative 375.9 meters x hat. Similarly, I'm going to look at this y component of this vector. Remember, I'm breaking down the red vector in angle magnitude form into an x part and a y part. Well, the y part is opposite the 20 degrees. So I get the magnitude of that y component. Look, I've got magnitude signs here, is equal to the magnitude of the entire vector, which is the 400 meters, times sine of 20 degrees, because the y component is opposite to the 20 degrees. And I get a magnitude of 163.8 meters. But I want this full-blown y component vector, so I need a direction. Well, look at the direction from the diagram. It's pointing downward. That is known as negative y hat. That is known as negative y hat. So once again, what have we done really, kids? What have we done? Well, we've converted from angle magnitude to component form. Negative 375.9 meters x hat. Negative 136.8 meters y hat. We've converted from angle magnitude to component. These two are just different ways of saying the same thing, different ways of expressing the same vector. But in component form, as you're going to see shortly, adding them is very easy. So remember what our question was here. We wanted to find this resultant vector right here in yellow. And we said, well, to find that resultant vector, I got to add the red vector and the green vector. I said, okay, 300 meters, 60 degrees north of east, plus 400 meters, 20 degrees south of west. Let's add them. And I said, well, okay, you got to add them vector tip to tail addition. The answer is not 700 as a magnitude, right? You got to do vector tip to tail addition. And it would involve cosine law, maybe sine law. It would involve opposite angle theorems and a whole bunch of other geometry to actually find this magnitude, right? And I said, let's do it in a different way. Let's rewrite these vectors in a new form. Instead of angle magnitude form to do this addition, we're going to use an xy component form to do the addition. That's a much more easier and convenient way of doing it. And here it is. I've written those two vectors again in in component form. We calculated these components, this one, this one, this one, just a few moments ago. Now you just add them up. It's like collecting like terms. Collect all the x's together. Okay, negative 225.9 meters x hat. Collect all the y's together. Okay, I'm collecting all the y's. Positive 123.0 meters y hat. And that is your answer. Okay, so your answer is so many meters in the negative hat direction, and to that we'll add so many meters in the y-hat direction to give us the final answer, vector tip to tail addition here, our blue resultant vector. This is the answer. There's nothing wrong with that. You're not used to writing vectors in this way, but this is the answer. Now, could we convert this back into angle magnitude form? Sure we could. We know Pythagoras, right? This would be A, this would be B, this would be C. We do Pythagoras and we can find the magnitude of the blue vector there. Very easy to do. It would be 257.2 meters. Could we find this angle here, theta? Yes, we could. We could use tan inverse of opposite over adjacent, opposite being the y component, adjacent being the x component. I could put it in here and I would get 29 degrees. I would get 29 degrees, right? And I would then get an answer of 257.2 meters, 29 degrees north of west. Or if you don't want to use that angle here, theta, you could use the complementary angle there, which would be 61 degrees west of north. They're equivalent. Remember, any 90-degree angle can be divided into two angles, the angle and its complement. So it doesn't matter which angle you use. But the answer would be 257.2 meters, 29 degrees north of west. This answer and this answer, these two answers are the same. They are equivalent. They're just different ways of writing the answer. I like this way better. Very easy to do. Don't have to get into drawing a scaled diagram and cosine law and sine law and a whole bunch of geometry, opposite angle theorem, Z rule, and all parallel line rule and the rest of it to find angles here, there, and everywhere. I just break everything down into x, break every vector into x and y, and then add all the x's together, add all the y's together, and you will have a certain amount x hat and a certain amount y hat. Find it to be very convenient. And now we also wanted to find the average velocity for the question we've been talking about. Well, the average velocity is the resultant displacement divided by time, right? The resultant displacement divided by time. Well, here it is, negative 225.9 meters x hat plus 123.0 meters y hat. Divide each of them by 80, and you'll get meters per second in the x, meters per second in the y. You just divided. The direction stays the same, negative, negative, positive, positive. You divide the numbers. There's your answer for the velocity. The velocity here is written in component form. Or you could take the angle magnitude form, do your dividing here. The angle stays the same. Now you've got meters per second, and you get 3.22 meters per second, 29 degrees north of west. Guess what, kids? These two answers are mathematically equivalent. This is written in component method, ordered pairs of x hat and y hat, and this is in the angle magnitude form. Absolutely equivalent. Component method, very important for the rest of this course. Know it well. This is the way.